Hello, welcome to the first in a series of videos on the A-level waves topic. I wanted to make these just to help you if you're struggling a little bit while we're not in school, just to help with some of those slightly more difficult concepts. So the first video here in this topic is going to be all about refraction. Now, you've done refraction at GCSE, so I'm going to start off by just recapping GCSE refraction and then build it up to the content that you need for A-level. So we'll start off then just looking at refraction as you knew it at GCSE. You can see on the screen that's a glass block. And so if I shine a ray of light through the glass block, as hopefully you know, it doesn't follow a straight path through the block. And you can see that our ray of light refracts towards the normal line as it goes into the block, and it refracts away from the normal line as it comes out of the block. Now you can see a little bit of reflection going on at each boundary, but generally, okay, it's refracting towards the normal line, refracting away from the normal line. And if I change the angle of incidence, you can see that the angle of refraction changes too. And the only place I can put this ray of light where I get no refraction at all is if I shine it straight down the normal line like that, then I get no refraction happening. Okay, just to draw that then as a summary, you can see that a light ray, if I draw the light ray coming in like this, okay, remembering an arrow to show its direction, it refracts towards the normal line. Okay, and then I could draw another normal line at the point it's leaving. I'm going to make it as accurate as I can. That's not particularly good, but you get the idea. And then it refracts away from the normal line and will end up going in the same direction it was to start with. Okay, so that's refraction happening. Now, I'm not going to go back into all the details in terms of the meaning of angle of incidence, angle of refraction. If you're not sure about that, you need to look back to your GCSE work. But we need to just remind ourselves of why this happens and then build on it. Now, essentially, the reason that the light changes direction is all to do with the speed it's travelling. So light travels different speeds in different materials. It travels fastest in a vacuum. As far as we're concerned for this, actually, air is pretty close to a vacuum. And so the light is slowing down as it goes into the block. You might think, why does that actually make it change direction? Well, we can use a bit of an analogy. You may well have heard this before. If we imagine over here then that this is the road, and then this here is some kind of any boggy marshland. There's some bits of plant here in the marsh. So this is a bog. Now, if we imagine here's a truck. We imagine this truck driving along this way, and it hits the bog. Now, as it hits the bog here, this right-hand wheel is going to slow down first. So this right-hand wheel is now travelling slower than the left-hand wheel, and that's going to mean that our truck changes direction. And then once both wheels are in the bog, they've both slowed down, and so now it travels along like this, slowly. And so what that's given us is it's given us that change in direction. Now that also explains why, if we imagine our truck hitting the bog head on, both wheels slow down together, and so it doesn't change direction. But what has a truck and a bog got to do with light? Well, instead of having the truck, just imagine the ray of light, and imagine it slowing down as it goes into the glass block. One side of the light ray slows down before the other side of the light ray, and therefore it changes direction. Okay, we're going to think now about something called refractive index. Now, obviously, it's my advice that you make notes on this as we go through. So let's think about what we mean by refractive index. It's essentially putting a number on what we just said and talking about how quickly light travels in different materials. But instead of just talking about actually what speed the light travels, we want to know how quickly does the light travel relative to the speed that it travels in a vacuum. So the refractive index, what it actually is it's the ratio of the speed of light in a vacuum to the speed of light in the material. Light in the material. Okay, now we can obviously write that as a formula. And so if we want to write it as a formula, well, refractive index is given the symbol n. So there's n for refractive index. And so since it's a ratio here, Speed of light in a vacuum we call c. Right, you'll have seen that before back in quantum topic probably, and the waves, wave speed when you talked about electromagnetic waves, divided by the speed of light in the material, often given c with a subscript s, I guess, for substance. So there's our formula for refractive index. N equals c, that's the speed of light in a vacuum, over cs. Now, c is given to you on the formula sheet, but hopefully you have sort of committed it to memory by now. C is 3 times 10 to the 8 meters per second. Okay, that's the speed of light in the material. And like I said, N over here is the refractive index. All right, so there's our formula. Now, it is worth noting at this point, I said earlier that as far as we're concerned here, air is pretty close to a vacuum, at least in terms of light. And so that means that the refractive index of air, well, if you think about it, if it travels about the same speed in air as it does in a vacuum, refractive index of air is approximately 1. And that's something that you need to know and becomes very useful later on. So refractive index of air, it's not actually 1, but it's pretty much 1. Right, the other thing just to remember is that your refractive index is always going to be greater than 1 or equal to 1, I suppose, in the case of air. But for a material, like our glass block, our refractive index will always be greater than 1 because light always travels quicker in a vacuum to what it does in that material. Okay, now one of the big differences between GCSE and A-level is that A-level you have to be able to do calculations in terms of angles of incidence, angles of refraction and so on. Now this is known as Snell's law. It's named after a Dutch astronomer called Willebrord Snellius, who had come up with this rule. I mean, actually a few people had come up with it before him, but they hadn't published it. And some people came up with it after him and were then accused of copying Snellius and so on. But it's known as Snell's law, named after him. Now, if we imagine then that what I've got here, this is a boundary between two materials, and it doesn't matter what they are, but the top one has a refractive index N1, the bottom material there has a refractive index N2. And I'm going to put a normal line on there, and we're going to say that I've got a ray of light that is hitting that boundary, and refraction of some kind is occurring. So there's my, what we would, I suppose, call the incident ray, what we would call that, and then here I've got what we would call the refracted ray. And so you may remember that we've got two key angles, remembering that the angles we're interested in are the angles between the normal line and the ray. So I've got this angle in here. Now, I'm going to call that theta 1, okay, because it's on the side of N1. And then I've got this angle in here. Oh, that's a theta, sorry, this pen's a bit thick. Theta 1 and theta 2. Now, okay, so Snell's law then just says that N1 times the sine of theta 1 is equal to N2 times sine theta 2. So that is Snell's law, and what that allows you to do is for any two materials, it allows you to predict the angles that the light ray will enter or will leave based on the rules of refraction. Okay, now let's imagine that I wanted to find the refractive index of this block. Now there is a reason I'm using a semicircular block rather than the rectangular one, and you'll see that hopefully in a minute why. So you can see I've drawn a little normal line on there, and what I'm going to do, I'm going to shine a light ray in, shine a light ray in, there it is, which hits the block at the normal line. So this would be much easier if you were using a pencil on a piece of paper, but I can draw a couple of marks here to show the light ray going in. And then obviously it hits out that normal line. Now the reason I've used a semicircular block is so it does not refract on the way out. And you can see actually this is not refracting on the way out, which means if I just put a couple of marks down here, that will show me the path of the light ray on the way out of the block. Okay, so I can remove my ray box now. I can actually remove the block as well. And if I join up these lines, and obviously if you were doing this on paper, you'd do it much neater than this with a ruler. There we are, that's terrible, but there we go. And then it comes down like that. Okay, now obviously that first line is meant to be a straight line. I've just drawn it really badly. But our angles then, so I've got here n1 and I've got here n2. I've got my θ1, that's going to be this one in here. And I've got my θ2 in here. Now n2 is what we're trying to work out. n1, well, that was in air, so n1 is 1. So I'll do my calculation down here. So I'll put my formula again quickly. n1 sine θ1 equals n2 times sine θ2. n1 is 1, that makes this a bit easier. So sine θ1, right, θ1 I've got to measure. Now, obviously, this is going to be very, very rough given my drawing on this occasion. But n1 is looking like, and I'm going to go very, very roughly 55 degrees. So we've got sine of 55 degrees equals n2 times sine of θ2. Now, sine of θ2, again, this is going to be extremely, extremely rough, just because of the limitations of what I'm doing. That is roughly 35 degrees. Okay, which means that n2 is going to be sine 55 degrees divided by sine of 35 degrees. Okay, and we can put that into our calculator and it will give me my answer. And so the answer in this case is about 1.4. Okay, now because, I should have mentioned this earlier, because refractive index is a ratio of speeds, it has not got a unit. It's just a ratio, so my answer there is 1.4. Now, that is one way that we could do it. As you can see, though, for this situation, if we make a tiny mistake in the drawing or in the measuring of the angles, we get a totally different answer. And so, although it's all right, that's not the best way to do it. And actually, if you were asked for the best way to work out the refractive index of a block, what you'd be better off doing is coming back to this sort of stage up here. Actually, I'll write it out up here. If m1 is always 1 in this case, you've got sine θ1 equals the n of the block, which I'll call n2, times sine θ2. And so if you actually took lots of different measurements for lots of different angles of incidence, so lots of different sine θ1, you could then plot a graph. Because if you plot a graph where sine θ1 is y and sine θ2 is x, that would mean that your gradient would then be n2. And your y equals mx. There would be no intercept. So you should get a straight line through the origin with a gradient of the refractive index.